The National Electrical Code (NEC) and industry best practices provide guidelines that should be considered when protecting vertical busbars in motor control centers (MCCs). Firstly, overcurrent protection is essential. The vertical busbar should be protected from overcurrents by a circuit breaker or fuse rated at or below its rated capacity. Secondly, coordination with horizontal busbar protection is important. The overcurrent device protecting the vertical busbar should be coordinated with the circuit breaker protecting the horizontal busbar to ensure that a fault in the vertical busbar will trip the vertical busbar protection before tripping the horizontal busbar protection. Thirdly, proper sizing is necessary. The overcurrent device protecting the vertical busbar should be sized to protect the busbar from short circuit and ground fault currents. Fourthly, adequate interrupting capacity is crucial. The overcurrent device protecting the vertical busbar should have an interrupting capacity that is equal to or greater than the available fault current at the location of the MCC. Now let's consider a specific situation. If the vertical busbar is rated for 300 amps and there's a plan to install a 300 amp breaker on the vertical busbar, in addition to two 150 amp breakers that are already installed, the following factors must be considered. Regarding horizontal busbar protection, since the main breaker is sized to protect the horizontal busbar, which is 600 amps, it is assumed that the horizontal busbar is adequately protected. Considering vertical busbar protection, the proposed 300 amp breaker on the vertical busbar meets the overcurrent protection requirement. As long as the 300 amp breaker is coordinated with the main breaker, it should provide adequate protection for the vertical busbar. It is vital to confirm that the interrupting capacity of the 300 amp breaker should be checked to ensure that it is sufficient for the available fault current of the MCC. Based on this information, it is generally acceptable to install a 300 amp breaker on the vertical bus in an MCC, provided that the following conditions are met. Firstly, the horizontal bus is adequately protected by the main breaker. Secondly, the 300 amp breaker is coordinated with the main breaker. Thirdly, the 300 amp breaker has adequate interrupting capacity. It is always recommended to consult with a qualified electrician to verify the specifics of any situation and confirm the appropriate protection measures. The primary goal of overcurrent protection for vertical busbars is to prevent damage to the busbars and connected equipment in the event of an overcurrent condition. Overcurrents can result from short circuits, ground faults, or overloads. If the busbar is not properly protected, these overcurrents can cause the busbar to overheat, melt, and potentially cause a fire or explosion. The overcurrent protection device, whether it's a circuit breaker or a fuse, is designed to interrupt the flow of current when it exceeds a predetermined level. This level is chosen to protect the busbar from damage while allowing normal operating currents to flow. The rating of the overcurrent device should be at or below the rated capacity of the vertical busbar. For example, if the vertical busbar is rated for 300 amps, the overcurrent device should be rated at 300 amps or less. Coordination between the overcurrent devices protecting the horizontal and vertical busbars is crucial for ensuring that the correct device trips in the event of a fault. The goal is to isolate the fault to the smallest possible section of the electrical system, minimizing disruption to the rest of the system. This is achieved by selecting overcurrent devices with different time current characteristics. The overcurrent device protecting the vertical busbar should be faster acting than the overcurrent device protecting the horizontal busbar. This means that in the event of a fault on the vertical busbar protection will trip first, isolating the fault and preventing the horizontal busbar protection from tripping unnecessarily. Proper sizing of the overcurrent device is also essential for effective protection. The overcurrent device should be sized to protect the busbar from both short circuit and ground fault currents. Short circuit currents are very high currents that can flow when there is a direct short between two conductors. Ground fault currents are low currents that can flow when there is a fault between a conductor and ground. The overcurrent device should be able to interrupt both types of currents quickly and safely. The interrupting capacity of the overcurrent device is the maximum amount of current that it can safely interrupt. The interrupting capacity should be equal to or greater than the available fault current at the location of the MCC. The available fault current is the amount of current that would flow in the event of a short circuit at that location. This can be calculated using various methods, including short circuit studies. If the interrupting capacity of the overcurrent device is less than the available fault current, the device may fail to interrupt the current safely, which could result in damage to equipment and injury to personnel. Now consider the specific scenario where the vertical busbar is rated for 300 amps, and there is a plan to install a 300 amp breaker on the vertical busbar, in addition to two 150 amp breakers that are already installed. In this case, it is important to verify that the existing main breaker protecting the horizontal busbar is adequately sized. If the main breaker is sized at 600 amps, as stated, it is assumed that the horizontal busbar is adequately protected. However, it is still important to verify this assumption by checking the actual load on the horizontal busbar and ensuring that it is within the rating of the main breaker. The proposed 300 amp breaker on the vertical busbar meets the overcurrent protection requirement, as it is rated at or below the rated capacity of the vertical busbar. However, it is important to ensure that the 300 amp breaker is coordinated with the main breaker. This can be done by comparing the time current characteristics of the two breakers and ensuring that the 300 amp breaker will trip before the main breaker in the event of a fault on the vertical busbar. Finally, it is essential to check the interrupting capacity of the 300 amp breaker to ensure that it is sufficient for the available fault current at the MCC. If the interrupting capacity is not sufficient, a higher rated breaker may be required. In summary, it is generally acceptable to install a 300 amp breaker on the vertical bus in this MCC, provided that the following conditions are met. Firstly, the horizontal bus is adequately protected by the main breaker. Secondly, the 300 amp breaker is coordinated with the main breaker. Thirdly, the 300 amp breaker has adequate interrupting capacity. However, it is always recommended to consult with a qualified electrician to verify the specifics of the situation and confirm the appropriate protection measures. This is because electrical systems can be complex and there may be factors that are not readily apparent that could affect the safety and performance of the system. A qualified electrician will be able to assess the situation, perform the necessary calculations, and recommend the appropriate protection measures to ensure the safety and reliability of the electrical system. In addition to the above guidelines, there are some other best practices that should be followed when protecting vertical busbars in MCC. Firstly, it is important to use high-quality overcurrent protection devices from reputable manufacturers. This will help to ensure that the devices are reliable and will perform as expected in the event of a fault. Secondly, it is important to regularly inspect and test the overcurrent protection devices to ensure that they are in good working condition. This should be done at least annually or more frequently if the MCC is located in a harsh environment. Thirdly, it is important to keep the MCC clean and free of debris. This will help to prevent overheating and other problems that could lead to overcurrent conditions. Fourthly, it is important to train personnel on the proper operation and maintenance of the MCC. This will help to ensure that they are aware of the potential hazards and how to respond in the event of an emergency. By following these guidelines and best practices, it is possible to ensure that vertical busbars in MCC are adequately protected from overcurrents, which will help to prevent damage to equipment and injury to personnel. Also, the selection of appropriate overcurrent protection devices for vertical busbars in MCC is crucial for ensuring the safety and reliability of the electrical system. Several factors must be considered when selecting these devices, including the rated capacity of the busbar, the available fault current, and the coordination requirements with other overcurrent devices. Firstly, the rated capacity of the busbar is the maximum amount of current that the busbar can safely carry. The overcurrent protection device should be rated at or below the rated capacity of the busbar. Secondly, the available fault current is the amount of current that would flow in the event of a short circuit at the location of the MCC. The overcurrent protection device should have an interrupting capacity that is equal to or greater than the available fault current. Thirdly, coordination with other overcurrent devices is essential for ensuring that the correct device tripped in the event of a fault. The overcurrent protection device protecting the vertical busbar should be coordinated with the circuit breaker protecting the horizontal busbar to ensure that a fault on the vertical busbar will trip the vertical busbar protection before tripping the horizontal busbar protection. In addition to these factors, it is also important to consider the type of overcurrent protection device to use. The two most common types of overcurrent protection devices are circuit breakers and fuses. Circuit breakers are reusable devices that can be reset after they trip. Fuses are single-use devices that must be replaced after they blow. Circuit breakers are generally preferred for MCC applications because they are more convenient to use and can be reset remotely. However, fuses may be a better option in some cases, such as when very high interrupting capacity is required. Once the appropriate overcurrent protection device has been selected, it is important to install it correctly. The device should be installed in accordance with the manufacturer's instructions and all applicable electrical codes. It is also important to regularly inspect and test the overcurrent protection device to ensure that it is in good working condition. In addition to the specific requirements for overcurrent protection, there are also some general safety precautions that should be followed when working with MCC. These precautions include, firstly, always to energize the MCC before working on it. Secondly, wear appropriate personal protective equipment, such as gloves and safety glasses. Thirdly, never work alone. Fourthly, be aware of the potential hazards and how to respond in the event of an emergency. By following these safety precautions, it is possible to minimize the risk of injury when working with MCC. It is also important to consider the impact of harmonics on the performance of the overcurrent protection devices. Harmonics are distortions in the sinusoidal waveform of the electrical current. They can be caused by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can cause overcurrent protection devices to trip prematurely or to fail to trip when they should. To mitigate the impact of harmonics, it may be necessary to use specially designed overcurrent protection devices that are rated for harmonic loads. It is also important to perform a harmonic analysis of the electrical system to determine the level of harmonics present and to select the appropriate overcurrent protection devices. In addition to overcurrent protection, it is also important to provide adequate grounding for the MCC. Grounding provides a low impedance path for fault current to flow back to the source, which helps to protect personnel and equipment from electrical shock. The grounding system should be designed in accordance with all applicable electrical codes. It is also important to regularly inspect and test the grounding system to ensure that it is in good working condition. Another important consideration is the ambient temperature in which the MCC is located. The ambient temperature can affect the performance of the overcurrent protection devices. Overcurrent protection devices are typically rated for a specific ambient temperature range. If the ambient temperature exceeds the rated range, the device may trip prematurely or fail to trip when it should. To mitigate the impact of ambient temperature, it may be necessary to use specially designed overcurrent protection devices that are rated for a wider temperature range. It is also important to provide adequate ventilation for the MCC to help keep the ambient temperature within the rated range. Furthermore, the altitude at which the MCC is located can also affect the performance of the overcurrent protection devices. Altitude affects the dielectric strength of air, which can affect the interrupting capacity of the overcurrent protection devices. If the MCC is located at a high altitude, it may be necessary to use specially designed overcurrent protection devices that are rated for high altitude applications. It is also important to consult with the manufacturer of the overcurrent protection devices to determine the appropriate derating factors for altitude. In addition to these technical considerations, it is also important to consider the cost of the overcurrent protection devices. The cost of overcurrent protection devices can vary depending on the type of device, the rating, and the manufacturer. It is important to select overcurrent protection devices that are cost-effective while still providing adequate protection. It is also important to consider the life cycle costs of the overcurrent protection devices. The life cycle cost includes the initial cost of the device, the cost of installation, the cost of maintenance, and the cost of replacement. It is important to select overcurrent protection devices that have a long life expectancy and require minimal maintenance. Finally, it is important to document all of the decisions that are made regarding the selection, installation, and maintenance of the overcurrent protection devices. This documentation should include the type of device, the rating, the manufacturer, the date of installation, the date of last inspection, and any other relevant information. This documentation will be helpful for future maintenance and troubleshooting. By following these guidelines, it is possible to ensure that vertical busbars in MCC are adequately protected from overcurrents, which will help to prevent damage to equipment and injury to personnel. Also, regular maintenance and testing of the overcurrent protection devices is essential for ensuring their continued reliability. This maintenance and testing should be performed by qualified personnel in accordance with the manufacturer's instructions and all applicable electrical codes. The maintenance and testing should include the following. Firstly, visual inspection. The overcurrent protection devices should be visually inspected for any signs of damage, such as cracks, corrosion, or loose connections. Secondly, mechanical testing. The overcurrent protection devices should be mechanically tested to ensure that they operate smoothly and correctly. This testing should include checking the trip mechanism and the reset mechanism. Thirdly, electrical testing. The overcurrent protection devices should be electrically tested to ensure that they trip at the correct current level and that they have the correct interrupting capacity. This testing should be performed using calibrated test equipment. Fourthly, documentation. The results of all maintenance and testing should be documented. This documentation should include the date of the maintenance or testing, the name of the person who performed the maintenance or testing, the results of the maintenance or testing, and any corrective actions that were taken. In addition to regular maintenance and testing, it is also important to have a plan in place for responding to overcurrent events. This plan should include the following. Firstly, identifying the source of the overcurrent. Secondly, isolating the overcurrent. Thirdly, repairing the damage caused by the overcurrent. Fourthly, preventing future overcurrent events. By having a plan in place for responding to overcurrent events, it is possible to minimize the damage caused by these events and to prevent them from happening again in the future. Remember to always consult with a qualified electrician when working with electrical systems. Electrical systems can be dangerous, and it is important to take all necessary precautions to protect yourself and others from electrical shock.